Hey guys, what's up? Today we're gonna be on episode 2. So let's make a new one. Okay, so now we're gonna learn about memory. So far, everything has inputs all the way to outputs, and there's like garbage in here that manipulates the inputs. But now, this is what we call combinational. But what if we send something back into itself? We never tried that before. It was always going forwards. But what if we send it back and we have inputs, but we still send it back? This is what we call, I don't know what it's called, but it's like a NOR gate going into a NOR gate, and we have Q, and then we have not Q. So let's make that here. In Minecraft, a NOR gate is not an OR gate. This is an OR gate. See? NOR gate basically means if it's zero. Means if it's zero, right? If the inputs are zero, it's zero. So what a NOR gate is just a NOT gate. Because in Minecraft, a torch can get many inputs. So a NOT gate with many inputs is a NOR gate. That's exactly here as well. So we have, like, let's say we have a NOT gate with 2 inputs. And then, like a NOT gate with, now we have a NOT gate with 2 inputs. The exact same if we were to build a NOR gate with 2 inputs. Bop, 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 bop. It's the exact same. So that's the logic that we will be using. So what if we attached a NOR gate into a NOR gate? So we take the output of this NOR gate, put it in the input. And we also need an input as well, because it's a NOR gate, we have like more than one input. I'm not saying 2 inputs, because it doesn't have to be 2. So let's see what this does. We usually read this as our output. So let's see what this does. Well, now that we're not doing combinational, we should start using buttons. So if we press this, it turns off and stays off. Press this, turns on and stays on. Does this sound familiar? That's because it's this thing. It's like the same as if we were able to like change the state through wires. In the circuit board game, you can. See how you can. But in Minecraft, you can't. See how you could change the actual button without actually touching it? It's the same thing. That's why in virtual circuit, we have it easier. But here, we have to do it the hard way. So, this is in Minecraft called a NOR latch, or a RS latch, or a RS NOR latch. So let's try to make it smaller. So we have a torch here. We could see that it goes around into the back of here. So we could do that into the NOR, and then we could do that. Is that really it? Yes, it is. Notice how we do that. Notice how we do that and it turns on, and then we do that and it turns on. This is one of the types of memory. But in Minecraft, we don't usually do this type of memory because we have this cool thing called comparator. Comparator has 2 modes where you could this is called compare mode, and this I might actually have to turn on my pack. So now we could see the numbers of the actual. See how it says 15, 14, 13 because it has like strength. So what it does, so normally without any input on the side, it's like a repeater, but we keep the input. See, if it was a repeater, just turns it into 15, which is the highest. Here it keeps it, no matter what state, unless we have something from the side. If the side is bigger than the back, it doesn't output. But if it's smaller, you'll notice how this is 13 and this is 12. It's 13. Now subtract, it's 1. Because 13 minus 12 is 1. Okay, so how can we use this to our advantage? Well, it's an AND gate. If you notice that we could just invert this and it's an AND gate, right? It doesn't do anything. It's an AND gate. So, with normal, and now I'm going to teach you about repeater locks. You can actually put repeaters from the sides. And what that does, so let's say we have this here, this here. So it normally works, right? When we lock this, has this thing, that means it doesn't accept inputs. But that's not it. If we stored it, now it's completely stored. It's locked in this repeater and will always output. This is enough to create a register. Registers like something that can like hold the setting, right? So like let's say we're adding a button here. So let's say if we wanted to store on, done, it's stored. And then we wanted to store off, done, it's stored, and the input doesn't do anything. But the issue with this is it's always, it's always writing. But if you have many inputs writing to the same wire, they will interfere with each other. So we need something that only writes to the wire if we want it to. So let's make that here. So this is if we want to enable, E for enable, and this is our A input. So if it's 0 and we don't want to enable, it's 0. If it's 0, we want to enable, it's 0. If it's 1 and we don't want to enable, it's 0. If it's 1 and we want to enable, it's 1. And this is an AND gate. So what we can do, we could attach an AND gate here. We can attach an AND gate to the wire, and it only turns on when we want it to. Is this a register? Yes, it is. But is it big? Yes, it is. Wait, it's kind of. It only reads the input when we want it to. Let's say we stored 0. We stored 0, and we want to read it. It's gonna be 0. But yeah, why is this still not good? Because it's big. So remember what I said about this is an AND gate, if you think about it. So we just attach it here. It's like a very small register, thanks to Minecraft God. This doesn't work like anywhere else. Because what this is, locked repeater, it's a D latch. You can like it's if you search it up, it's a D latch. It's the same thing. You could just copy the see the NOR is still there, the enable, it's the same thing. But like Minecraft is simpler. Okay. So now Let's store 1 and read 1. Nice. Now let's store 0 and read it. It's going to be 0. So the cool part about this is that we can have many registers going into the same wire. So yeah. So these are all registers, different registers, but when we want to select which one goes on the main wire, which we call a bus, we can. Not all of them go at the same time. So let's say we want to store 1 here, and 1 here. Alright, so we want to read this one, it's nothing. We want to read this one, it turns off it to 1. We want to read this one, it's nothing. This back wire is called a data bus. And in the computer, you have to be very careful that only one output is on it at a time. See here, you can notice that these 2 wires are data buses. They condense like all these wires down. It's a virtual circuit board thing. But here you could see that how there are AND gates for every single part that's being displayed on the wire. There are AND gates. Because we have to choose every single time. And there cannot be 2 things on the wire at the same time. That's how everything works. So let's say, so we could stack this so many times, and we could stack these individual ones up and read all of them at once so that they turn into, am I recording? They turn into like, each of these columns can spit out like a whole word. But if it's 8 bits, it's called a byte. But call it a word. So and we call it a register file. So let's say we have a register, bank, or file, whatever here. Regs for registers. So we can input data, and we can also input read data, read from a register, or write to a register. And out comes our data. Is this enough to make a computer? No. Remember our ALU from last episode? Well, we also need to attach an AND gate because we don't always want it to be outputting on a bus. So here there's an invisible AND gate because it's inside the register. So this is all shared. It's even shared inside the input. It's even shared inside the ALU input. And this is if we want to sub. And this is if we want to read from the ALU. So we have these 4 control wires. Read. Well, this read actually comes from here. So we have read LU, which means output. So LU out. We also have sub. Which could be SU. We have register in. Read means out. So register out. And write means register in. Like it opens the input. And we know how to open the input. We can open the input with this, and we can output it with this. So we have in. So we have these 4 control wires. And we can do simple instructions. So let's say we connected them all to the start. So to connect to all these four. This is our control word, and I don't feel like spelling that out, so I'm just gonna right here. It's also its own bus. As you can see, I have like so many buses. These two are the data. I'm not gonna touch it actually. Two data buses, two, four, six instruction buses. Because only in virtual circuit board, only 16 things can fit on one bus. So I need like multiple when I want more. So this is our control word. And we could make simple instructions with just these four things. So let's say we have like a file saying what's in every register. So at register, each register has an address. So if we write the address here, like we say write data to 4, it looks at 4 and replaces it with whatever is this. So let's say right now in this state we have, let's say we have 2 in register 0 and we have 3 in register 1, and these are nothing, which means they're all 0 because they're all cleared. This is our register file right now for this operation. Okay? And let's say what we want to do for the first cycle or like iteration, oh well, I guess you want to add like 2 registers here. So one is for the A input of the, and one is for the B input, and they also have their, but they're always going in the LU. They don't have like a enable to go to the LU because we always wanted to calculate, just not always output. So we have data bus going into LUA and LUB, and we have those control lines as well, LUA and LUB. So we need to add this. So the first input, the second input. So in the first, let's say we want to make a program. This is our loop. It's called a data loop, and I should probably make it cleaner. It's our data loop. Data loop. It's basically a computer. Just without, I didn't show you the decoders and stuff. This is our registers, and this is our LU. It has, let's say the registers are already inside the LU, the A and B registers. And the enable is also inside the LU. Okay, so we have regs. So this is basically what it is. So the data is always passed around, going all around the computer, going in and out. Alright, and then we have these 6. So we have LU out as a control line. We have subtract as a control line. We have registers out as a control line. We have registers in as a control line. We have enable or input A in as a control line. We have B in as a control line. So this is our control word. So we can manipulate. We could turn these on and off to like, yeah. This is our data bus going all around the place, inputting and outputting. How this works, why does this work? Because remember, in here, we only let it input into the register when we want it to. So right now, we're inputting it, but the registers doesn't really care about it yet. Because we're not letting it care about it yet. So let's say we want to make something that can add register 0 and 1, whatever is inside register 0 and 1, and put it in register 2. So the first one, we say register out for 0 for register 0, out 0. Put 0 on the bus. Put whatever is at 0, which is 2, on the bus. And put it inside A. And then now we take out for whatever is in register 1 and put it in register LU register B. And the LU will already calculate that. So we take what's out of the LU out, put it back, so registers in for 2. Now I could build this, but I don't feel like building it. Just understand that this does work. So following this, so in the first iteration, so let's say we can peek through as well what's inside A and B. So cycle 0. Take 0, put it in A. So now A is 0, 0, 1, 0. And I guess we want the LU output here. Now it's 0 for now. Take 1, put it in B. So that's 0, 0, 1, 1. Take that. So right now, in this moment, in this exact moment, it already has the inputs. So it knows the LU is automatically doing it. We don't have to tell it to calculate. But we have to tell it to output it. But it's already calculating. So 2 plus 3 is 5. That's what it is. In this cycle, it gets that. So in the next cycle, we read it. We don't read it on the same cycle that we inputted it, because it needs one cycle to calculate it. So we take the output, put it in 2. So 2 turns into 0, 1, 0, 1. That's a simple program. That's all there is to it. You may need a decoder, and actually I feel like explaining that. Because right now, registers, we don't know how to turn. Like, I'm just gonna build this in Minecraft just to show you. Like, we have these registers, right? We can turn on anyone we want to read, but we don't know, right? Let's say this is 3 in binary. We don't know how to turn this 3 into this third register, right? Because this is 0, 1, 2, 3. How do we turn this number 3 into this register? It doesn't know that yet. I just took it for granted here because it was very simplified. We do that with the decoder. So what a decoder does, it gets many inputs, a word that can have more than one turned on, turns it into something that can have only one turned on. How do we build that in Minecraft? That's a good question, because I kind of forgot. Alright, so we need to learn about complements to make a decoder. So you already understand this, I could erase it. Complements. So this is A, and A's complement has a hat. That means it's not A. We could also write not A like this, or not A like this. These all mean the same thing. Just let's know that we need a way. Remember what I showed you in the last episode where I can have like many inputs? So we can have like B here and A here, and then there are AND gates that snatch them. Do you remember that? Right? You remember that, right? But we also, in order to like, okay, so for A and B being binary, there are four combinations. There are four combinations for 2 digits in binary. 0, 1, 2, 3 in binary, right? How do we know that there are four? Because there's a calculation, right? For any base, it's base 2 now. Take it to the power of digits. And that's how many possibilities there are. So let's say for base 10, 2 digits, we have 100 possible things from 0 to 99. But now we have four, right? These four. We want to make it so that this turns on if it's 0, 0. This turns on if the input is 0, 1. This turns on only if the input is 1, 0. This turns on if only the input is 1, 1. Right? So this can turn on. We can get 1, 1 from here, or actually from here to make it cleaner. So we take A and B. Here, we should make it only on if not A and not B is on. How can we do that? We need a NOT gate going into this wire. That's a bad way to show it. That's also a bad way to show it. We need a NOT gate going into this wire. So this is the wire turns on if it's not A. This wire turns on if it's B is 0. This wire turns on if A is 0. So we need to know if A is 0 and if B is 0. Right? This one turns on if A is 0 and B is 1. This one turns on if A is 1 and B is 0. So this is our decoder. So let's make this in Minecraft. Later I will explain how De Morgan law simplifies this. Because as you remember, not before the AND turns it into NOR. And NOR is just not. So I'll show that later. But for now we're doing it complicated because you're stupid and I have to teach you. So we have the A inputs. So this is gonna be our B input. So we have B and its complement, which means it's negative version. And we also have A's complement and just A. Wait, how did I do that? Right, so these lines are exactly what I was talking about. So if B is on, you see? It's very cool. And we need 4 AND gates here. So let's make 4 AND gates. right? It's very, very simple. Very simple. Very simple. Very simple. Very simple. Very simple. It's very simple. No. I'm using something called World that it makes stuff easier. Um, we might have to use a repeater here. This is using the same logic I did for the carry out, which I actually don't know where it is. Right? Look, we have to like make bridges. It's the exact same. It's just decoding every possibility, but without an OR gate at the end. That's something for later. This is like it's related to a PLA. So the first one, we want to take it only if A's complement is on. Well, let's learn from our mistakes and do that instead. Oh no, we cannot do that. If A's complement is on, and B's com if A's complement is on. Okay, now the second one. That's 0, 1. We take which ones are on and put them in this AND gate. So we take this one because it's on, put it in this AND gate. And take this one because it's on, put it in this AND gate. Okay, now we take 1, 0, find which ones are on, put them in that AND gate. So we have this one here. This thing here. And it dies off, so we put that here. And we take this and just put it directly. And then last but not least, we just take the normal inputs and put them in this AND gate. What the? And then this input. So this is our decoder. So when it's 0, first one turns on. 1, second one turns on. 2, third one turns on. 3, third one, fourth one turns on. This is our decoder. Perfect. How do we simplify this? So, let's learn about ways to this tool that I'm about to show you will help us simplify lots of circuits. Hold on. So, we can say with like math that A and B is the same as um not of not A or not B. Do you remember this from the Morgan law? This is saying, so we take not A, so we have A and B here. We take the not of both of them, put it in an OR gate, which I'm just gonna merge the wires because that's what it is, and then put a not gate at the end, and apparently this makes an AND gate. And it does, because I already showed that like 20 times. I'm not gonna do it again. Look here. Not or not. But we can use this to simplify the fact that. So let's try it out. So let's say for every input we want, we take what we wouldn't want and then OR it and then invert it at the end. Let's try that. So mm, yeah, we take what we not want. So let's say we have 4 lines here showing what we have. This is our complement. This is our base. This is our complement. And we can use levers to show that this is B, this is A. Ba, ba, and repeaters here. This is the same thing as that. So we just extend it. We just extend these out. And I'll just stack these because I don't feel like doing the work. And the whole thing should be moved a little bit so that it may not interfere with this. Okay. Whoa. Yeah. Man, technical difficulties. Oh, so what we could do to simplify this is, so normally for, let's say for 0, right? We take this one and this one. So we would take this one and this one, right? Since we want the not of it, we can use these torches. And the torches will output down. See? When it's 0, it returns 1. So we have the invert the input part done for us with torches. Right? And we want to OR them together. So what we could do, we could just put them in the same line. We don't need this second line. See how these two go, this torch and this torch go in the same line, right? And then we invert the end. This is our AND gate. But it's much smaller. It's much smaller. See, so it's only on if it's 0. Isn't that cool? And we do the same thing for the rest. So, wait, first we need to probably stack this. Um, so now we have 4, right? So we take when B is on, and that's off. And then when we want B to be off, and that to be on, and when we want both to be on. So this is our working thing, right? 1, 1. This is our decoder, right? Yes. But if we want to simplify it even further, we can, we don't, in Minecraft we won't need a line and then its complement. We only need one line and only invert it in spots that we have to. So I think it's this. Bruh. yeah, as you can see here, we have our decoders. We did not invert the output, so let me just do that quickly. Alright, so I'm just gonna do that for now. So let's say when we want 1 to be on. So, if we want 1 to be on, that means we would need not 0, not A, not B, not C, but D would equal our first input. That's exactly what it's doing. See, for 1 to be on, we're seeing. So, in this convention, we use torches to represent 1 and a repeater to represent 0. So, 0, 0, 0, 1. 0, 0, 2, 1, 0. 0, 0, 1, 1. 0, 1, 0, 0. This is binary counting all the way to 15. Very small and very nice. In, in virtual circuit board, we don't really do that here, as you can see. I'm gonna try to explain this as best as I can. In virtual circuit board, we do have two lines for the NOT and its normal one, so this one and its complement, and we have NOT gates. That's what it is, right? These wires right here are NOT gates, or NOR gates. They're the same thing. NOT gates right here. We use it to go across. They are the same thing. If we look at it, this way, it's the same thing. You could see this is the NOT and this is its buffer. This is the buffer. This is its NOT. Right? So we could see how like we only breed to the NOT gate in places that we wanted to, and don't worry about this other half. That's what I'm going to talk about right now. Actually, I'm not going to talk about it. So that's how we decode it, and yeah, I think that's pretty much it to it. Oh, I also need to explain Boolean algebra. So, normally we would write equations like this, but having to write not a, and or is very complicated. So, what we can do, we can replace or with a plus sign. And we could replace not with a, so not B would be this. Or you could do this if you're weird. Or you could do this. Or you could do this. But any one of these works. And you could just merge the letters to mean and. Because what and is, it's just multiplying. It's just multiplying. And in real math, multiplying the same as just merging. So these are the same. So this means and, this means or, and if you're weird, you think that this is XOR, but actually this is XOR with the circle around it. This is XOR. So we could make this equation be not A plus B. This is our and equation, right? Or we could do something like this. I think this is the way you can do it. I think that's how you do it. I don't know. Or you could do like replace it with like A plus B. And it follows the same like brackets, exponents, add, subtract, like it follows those same order of operations. So and comes before oring. It follows the same thing. And now we need to learn about hexadecimal. So in base 2, we have 0, 1. In base 10, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is our base 10. But let's say we want to go more. Let's say base 16. So we have 16 digits. Let's just use letters as like a placeholder for these digits that we made up. So this is our base 16. We can store 16 in the same value. So 0f into decimal, which is base 10, is 16. When f is the biggest number, so we carry it over, is 17. This is hex. To represent that we're using a hex number, we use 0x, and then our hex number, and then we can use 0d to represent that it's a base 10 number. So ff would be um so 16th place, 16 times 16. I'm not doing all that. 0xff. It's it's not telling me. 255. This is 255. So we have 0d 255. Or in binary we can say 0b for binary. 1111111. The special part about the relationship about hex and binary is that we can, let's say we have this big binary number, 8-bit binary number. Let's say 0b is our big binary number. Since we could split it into groups of 4, since hex, a decimal can take 16 numbers, 4 digits represent 16 numbers. This is 9, and this is 9. So this is hex for 99. If you search up 0x99, it's 0b1001. 0x99 to binary. See, that's what I said. So I think that's all I have to say. I think that's pretty much all there is. I explained like the whole computer and how decoding works, and RAM is just the register file, but a lot of registers, and that's like the whole computer. And in the later episodes, I learned how to program the stuff in the computer. In the later episodes, I learned how to program the stuff in the computer.